We'll go ahead and get started. And so you should have just been notified that this session is being recorded. I just want to make sure everyone is aware of that. And I want to take a couple of minutes, or a couple of seconds, just to take care of some housekeeping. So as I mentioned, the program is being recorded. We have muted your mics. So that means that if you have any questions throughout this evening's program, to please use the chat for questions. Shira Greer is a history assistant at Woodlawn, and she's helping us put this program on, and she's the one that's going to be taking your questions and getting them to Shauna and myself. So if you have any questions, just make sure you leave them in the chat. So that's kind of some of the real quick housekeeping announcements before we dig into all of this stuff. And I want to welcome you to this evening's program. I'm Sean Halifax. I'm the new executive director at the Woodlawn Pope-Leighey House here in Alexandria. I'm super excited to be here and super excited to have moved to Northern Virginia, and looking forward to this evening's event and learning more from our educator, Shauna, who I'll introduce in just a moment. And learning also from some of you too. So this evening's virtual event is entitled Space Through Time, Humans in the Sky, 1781 to 2021. And we're going to take a timeline look at the changing night sky, advances in astronomy, and the history of Woodlawn and Pope-Leighey House over the last 240 years. We're doing this to help NASA, who has generously provided support for this program, mark the launch of the James Webb Space Telescope later this month. JWST, as it's referred to, will be the premier observatory for the next decade, and will study every phase in the history of our universe. At least we hope so. Of course, I'm not the person who will be guiding us on tonight's journey through time and space. I'm joined by Shauna Edson. Shauna is an astronomy educator at the Smithsonian National Air and Space Museum in Washington, D.C. She helps visitors use telescopes at the museum's public observatory and leads interactive astronomy programs such as planetarium shows. Tonight, we're using a software called Stellarium. Shauna will tell you more about it. It's really cool. I'm excited for you all to be able to see it if you haven't. She's on the design team for the museum's new exhibits about the solar system and astronomy, which will be opening soon in a few years. So I'm going to turn it over to Shauna.
Hey, thank you so much, Sean and Shira and Woodlawn Pope-Leighey House for holding this event to celebrate the sky and the upcoming launch of JWST. So this is a new space telescope that really will be looking back in time. It's going to allow us to see some of the farthest and faintest galaxies in our universe, newest forming stars and planets, and observing all those things is going to help us better understand really our origin story. How did our galaxies and stars like the sun form? How have they changed over time? What drives the formation of planets like the Earth? All of which led to us being here. So, I love how the sky, the heavens, the stars have often been integral parts of the origin stories that we tell as humans. And that's true both scientifically and culturally. So, as this launch approaches, I've really been thinking about how the sky has always been there and humans have always looked up at it. And so some of the things that we've seen in the sky have remained pretty constant over human timescales. Some of them have sort of changed slowly. And then there have been a few moments that really just caught everybody's attention. So today, Sean and I will be taking you through this journey of the last 240 years or so, noting some significant moments for the Woodlawn property and also things happening in the sky over that period of time. By exploring how these celestial and human stories are intertwined, we hope to set the stage for where JWST will hopefully take us from here. So let's start with the property that is now the Woodlawn and Pope-Leighey House.
Thanks, Shauna. Well, Shauna, George Washington acquired Mount Vernon in the 1750s, and for the next 30 years or so continued purchasing land around the area, so that by the 1780s, he owned about 8,000 acres at Mount Vernon, which he divided into 5 different farms. One was called Dogue Run Farm, which later became Woodlawn. Dogue Run, today it's referred to as Dogue Creek, Dogue Run Farm were named after the Doeg people, the indigenous people that occupied what is today Lower Fairfax County, until the land was occupied. Was granted to English colonialists, including Washington's great-grandfather in 1674. The word granted, however, is a euphemism, I think, from the Dogue people's perspective. For them, granted land meant their removal. The 1780s were a pivotal point in our nation's history. And in 1781, I doubt that George Washington was spending much time at Mount Vernon or at Dogue Farm. He was leading the Continental Army. And at the beginning of the year, Washington is on record expressing his fears that if the tides of the war did not soon change, public support for it would soon dry up. By March, the tide began shifting. In fact, on March 8, 1781, the French general, the Marquis de Lafayette, under orders from Washington, was not far from here. He was in Annapolis, and over the coming days sailed down the Chesapeake on his way to Yorktown, where the most decisive battle of the American Revolution would be fought only a few months later. Shauna, what would Lafayette have seen if he peered into the night sky that week in 1781 as he sailed so close to Dogue Run?
Well, let me show you. So this is the program that Sean mentioned. This is Stellarium. This is an excellent free software program that I believe Sherry will be putting the link in the chat for. This is something that you can play with, and I really love it as a teaching tool and just an understanding the sky tool. So you'll notice I've set the time and date. So it is March 8th of 1781. And we are in Alexandria, Virginia. We are at the location of the Woodlawn site. And here in the sky, there's a few things I'll sort of orient you. So we have these letters across the bottom. So S is south. So these are the directions. So we've got south, southwest. And we've also got sort of a picture that serves as the horizon. So this is a picture of a town in France. So sort of grass and trees, but it allows us to tell which way is the ground and which way is the sky. And so I can move and change where we are looking. So those direction markers are very helpful. The horizon is helpful to kind of know where we are. And I can also zoom in if we want to look at something more closely, or I can zoom out to see a little more of the whole sky. It does this sort of fisheye effect, but that's because we're trying to project a three-dimensional thing on a two-dimensional screen. And this is showing the known positions of stars, planets, the moon, based on our understanding of their locations and their motion. So where are they? How are they moving or orbiting? And then we can go backwards or forwards in time. This program can go up to 100,000 years into the past or the future. I will be sticking to these 240 years, but again, it is called Stellarium, and it is available for free online. And I encourage any astronomy enthusiasts or astronomy curious folks to play with it. But right now we are seeing the sky from the Woodlawn area in 1781. And what Lafayette would have seen would be a pretty magnificent sky. So at this point, there were no bright streetlights to speak of. So there's no light pollution. There's all of these stars from the very bright to the fairly faint, and they can all be seen. Some of you may have noticed Orion here. So we've got the 3 stars of the belt and a few other bright stars. Orion would have been in his sky. And he also would have seen this sort of fuzzy band here across the sky. So as all of this was happening in North America, at the same time, across the Atlantic, 2 German siblings, William and Caroline Herschel, who are astronomers, were making a systematic map of the sky. They had a 20-foot telescope, which was one of the largest in the world at the time. And they were going just across the entire sky, counting how many stars they could see. And they found more stars in some direction. So in this bright band here, looking in this direction, there's a lot of stars here. But then if we move over in this direction, there's not quite as many stars in that direction. So presuming that their telescope could see to the edge of the universe, they figured, okay, in each direction, if I'm seeing more stars, that means that the universe must extend farther in that direction. So they made this survey, counted these stars, and used that to essentially build a map of what they understood to be the shape of the universe. And what they found was this sort of pancake or flat disk shape. There were a lot more stars in this one band and fewer in these other areas. They didn't realize that at the time, what they had actually found was the shape of our Milky Way galaxy. And we now understand that our Milky Way galaxy is this swirling pancake with hundreds of billions of stars and nebulae and star clusters and planets, very much like our own. So the idea, this concept that we are part of this swirling sea of stars that is organized into a galaxy, that the universe isn't just randomly scattered stars, but it is organized into these galaxies, that's a really fundamental structure of the universe. And so how these galaxies formed and how they evolved is a big piece of our origin, where we come from, and it's a big part of what JWST will hopefully be teaching us about. So that is our first stop on this little journey, and the next one is in 1803. So in 1803, this is when the first gas streetlights were introduced in the United States. So the night sky view was still quite good, but I'm going to adjust the light pollution a little bit, and I'm going to drop the Milky Way brightness a little bit, because when there were more bright lights in the night sky, it changed what people could see. And so also at this point, when someone looked up in the sky, they might have seen a balloon, because about 10 years earlier, the first hot air balloon had been launched in North America. It was piloted by French inventor Jean-Pierre Blanchard. And in a connection to the Woodlawn site, George Washington himself was actually present for the launch of that balloon. It lifted off from Philadelphia, and it traveled about 10 miles, and then it landed in New Jersey. So this balloons, this new way of traveling, ballooning became this sort of nationwide spectacle. Balloon mania became a thing. People were watching balloons as sort of exhibitions and such. So it was this new way of traveling, but it was definitely not as safe or as well understood or as controlled as, say, traveling by ship.
You know, Shauna, it strikes me how so much having to do with flying is associated with sailing. And when you mention hot air balloons as a new way to travel, it makes me think about how old gives way to new, and how the new sometimes can overshadow some pretty ugly things that are in plain view that need at least acknowledging. While we recognize the steps balloons took in bringing us one step closer to the stars, I can't help but think about how the old way of getting people about, those sailing ships, were the means by which millions of Africans, torn from their homes, their families, their communities, their cultures and civilizations, were forced into the Americas to be enslaved at places like Woodlawn. Beginning in 1800 and going through 1805, it was those enslaved men, women, and children that were forced into constructing the Woodlawn Mansion for George Washington's stepdaughter and nephew, Eleanor and Lawrence Lewis. Washington had gifted his Doe Creek farm to them upon their marriage, and they renamed it Woodlawn. But not only did they receive land as a gift, and this is something that's really hard for me to comprehend in the 21st century, I think, they also received people as wedding gifts. The people that Lawrence and Eleanor enslaved included people like Lucy Lee, David Gray, Peter Twine, some folks who we only know their first names, like Hanson, Dulcie, Suki, and so many more whom I only know as names right now, but I'm looking forward to learning more about because they have stories to be told as well. They have families here in America, but also in Africa. It's likely that some of the people enslaved by the Lewises were from the Angolan region. According to the Virginia slave statistics, during the period from 1712 to 1772, nearly 30% of all enslaved Africans of identifiable origin in Virginia were from the Angolan Congo River region of Africa. And for the 12-year period from 1760 to 1772, 50% were from the Angolan and Congo region. And one of the things we know is that George Washington was one of those men of his time that was also engaged in the Atlantic slave trade. And so it's very possible that the people that he was in the business of buying and selling were from this Angola and Congo region. But despite being stripped of so much of that these people carried, but despite being stripped of so much, these folks carried with them knowledge and memory. They would have brought with them their understanding of the sky, even as they were seeing something unfamiliar, such as North Hemisphere constellations. Shauna, what can you share with us about what they could have been bringing with them about the night sky?
Well, like you said, knowledge travels with people. So amid the really cruel circumstances that you just described, the people from Angola and Congo who were brought to this area would have carried their understanding of the sky and their ability to observe the changes as they moved northward. So I'm actually going to take us to Luanda, Angola, to see the sky there at this time. So it is a few hours earlier, so I'm going to take us back a little bit. So here in Angola, we are in the southern hemisphere. We can still see Orion. So that is something that they would have seen from their home and also been able to see here in Virginia. But then there are these other things. There is these 4 stars many of us know as the Southern Cross, and that's something that they could see from there, but they wouldn't have been able to see. They would have lost sight of that once they were brought north. And there are the star patterns, there's the sky they could see, and there's also, again, this notion of origin stories. And while Angola includes many different cultural groups with their own histories, I want to share one story that connects people to the sky. This was shared with me by Marco Romero, who is an engineer with the Angolan space program. So the story goes that the Ovimbundu people describe the origin of the first human, Feti, who is named the Beginning. He was a man who fell down from the sky onto the earth and began to explore and hunt, but he became really lonely because he was the only person here. And when he traveled to the Cunin River searching for a hippopotamus to hunt, instead, by the river, he saw a human figure rising out of the water. And that turned out to be the first woman, who he called Choya, or perfection. So the two of them, from the sky and from the land, became the first family from whom all of the Ovimbundu are descended. And so, as is true for many cultures around the world, this understanding, this story, this knowledge ties our human origins to the sky, to the universe. And in many ways, we are still looking to the sky for some of those answers, at least the ones that scientific inquiry can give us. So that is, looking to the sky for our beginnings. We have also looked to the sky for signs of endings as well as beginnings. And that actually takes us to our next stop, which is in 1833. I'm going to take us to November, because in November of 1833, this was what is known as is the Great Leonids meteor shower, also known as the night it rained stars. So people in North America at that time would have seen something like this. It was thousands of meteors per hour. It really, many people truly thought the world was ending. And so I have a story that I really love. This is from Walt Whitman's 1882 collection. And it's a connection between this event and our Alexandria, Virginia area. So it's titled A Lincoln Reminiscence. In the gloomiest period of the war, he had a call from a large delegation of bank presidents. In the talk after business was settled, one of the big dons asked Mr. Lincoln if his confidence in the permanency of the Union was not beginning to be shaken, whereupon the homely president told a little story. When I was a young man in Illinois, said he, I boarded for a time with the deacon of the Presbyterian Church. One night, I was roused from my sleep by a rap at the door, and I heard the deacon's voice exclaiming, Arise, Abraham, the day of judgment has come. I sprang from my bed and rushed to the window and saw the stars falling in great showers. But looking back of them in the heavens, I saw all the grand old constellations with which I was so well acquainted, fixed and true in their places. Gentlemen, the world did not come to an end then, nor will the Union now. And I have always found that story it has always moved me, this profound connection between the sky and humanity. And the fact that the people who witnessed this lived through something that was really terrifying and it impacted them. And yet they found solace in the things that remained unchanged. And I think about that in uncertain times.
Sean, I think, that they did, I'm sure. But as an enslaved person, the power to control so much of one's destiny meant that at any moment, the sky could fall and the world could become unrecognizable. Like when 24 enslaved people were sold by the Lewises and taken to Louisiana in 1836. I just moved here last week by choice from the Deep South, and I know firsthand how unsettling such a move is. I can only try to imagine what such a move must have been like for these 24 who had no choice. What's so astounding to me is that despite this traumatic event, which was common for so many to experience during this period, they endured. Theirs is a story of resilience and survival and is to be celebrated along with the acknowledgement of the tragic experience they endured, despite the physically and emotionally violent disruptions to their lives.
Absolutely. Yeah. And, disruptions happen in people's lives and they happen in the sky too. And that actually takes us to our next stop, which is in 1859. And this is the strongest solar storm and magnetic field disruption on record. And it's known as the Carrington Event. So on September 1st, 1859, British astronomer Richard Carrington was studying the sky. So he had a telescope pointed at it, and he was projecting that telescope's image onto a sort of white sheet. So that allowed him to see sunspots, to sketch them. There are a few sunspots depicted in this view. And on that day, there was actually a really huge sunspot group that was right in the center of the sun, sort of pointed at the Earth. And so he's sketching this and he's watching it. And then he saw these two bright beads of light that appeared on the sunspot group. And they were there for maybe 5 minutes and they shifted and faded. And he had no idea what he'd just seen. But he had just witnessed the first ever observed solar flare and the largest solar flare that we know of. And he just happened to be watching at the right time. So he caught it. He also had no idea that alongside the bright energy release, the light of that flare, the sun had also unleashed an enormous eruption of particles, almost like a sneeze, a giant sneeze through space. And this cloud of particles was rocketing toward the Earth at about 3,000 kilometers per second. That'll get you from San Francisco to New York in like 2 seconds, very fast. So 17 hours later, when that flood of solar particles crashed into the Earth's atmosphere and magnetosphere, it caused huge effects worldwide. The auroras, sometimes called the Northern Lights, were so bright, even in places like New York City and Washington, D.C., that you could read the newspaper at midnight by the light of them. Sailors as far south as the Caribbean were reporting the ocean looking like blood because it was reflecting this blood red aurora in the sky. Compass needles all around the world were shifting and changing in ways they'd never done before because the Earth's entire magnetic field was just reeling from the impact of these solar particles and the magnetic fields they brought with them. Telegraph lines were really the only long wires at the time, but there was so much energy in the Earth's disrupted magnetic field that was pushing these super strong currents through the telegraph lines. In fact, Mr. Fred Robes, who is a telegraph operator in this area in Washington, reported the following. I had been working combination to Richmond and had great difficulty from the changing of the current. It seemed as if there was a storm at Richmond. Concluding that this was the case, I abandoned that wire and tried to work the northern wire, but met with the same difficulty. For 5 or 10 minutes, I would have no trouble. Then the current would change and become so weak that it could hardly be felt. It would then gradually change to a ground so strong that I could not lift the magnet. While the aurora lasted, the same phenomena were observable. There was no rattling or crackling of the magnet, as is the case in a thunderstorm. So people like Mr. Roves and others recognized that something new and strange and really big had happened. This was really the beginning of us understanding the energetic and magnetic connections between the Earth and the sun. And had he not been watching and seeing that solar flare ahead of these worldwide disruptions, it would have been decades possibly before we made that connection. So it was this huge disruption that was just observed in many ways all over the world.
Shauna, perhaps no greater disruption to people living in the United States as the 1850s closed out was the secession of states from the United States and the outbreak of war in 1860 and 1861. But the disruption started here at Woodlawn a few years before. Following Lawrence Lewis's death in 1839 and his wife Eleanor's leaving, the property was purchased by Quakers in 1846. Who, along with free blacks, created what can be described as a community of business disruptors in the Old Dominion. The two groups of people created an experiment that was an integrated and free agricultural community to demonstrate that the economy of the United States, which depended on slavery as its bedrock, could be done away with. Slavery could be done away with. This community was such a disruptor that when the voting citizens of Fairfax voted on secession in May of 1861, 3 of the voting precincts in the county voted not to secede. In the Accotank precinct, in which Woodlawn is located, 76% voted against secession. I grew up and was educated here in Virginia and always taught that the Civil War was about states' rights. But as I got older, I learned that there was one particular right some states were concerned about most. In fact, they were quite clear and emphatic about it: the right to enslave another human being based on the color of their skin. Whether one believes the war was about states' rights, slavery, the Union, or whatever, it cannot really be argued that for the millions of blacks in the United States living at that time, the war was about their liberty, the same liberty the nation's founding fathers had found to be an unalienable right. I suspect that if all the free individuals in the district could have voted, it would have been an even greater margin against secession. But it wasn't until the Reconstruction Amendments were passed following the American Civil War that Black men could vote, and then only for a short period of time during Reconstruction. Following the end of Reconstruction around the 1870s, many whites engaged in acts of voter disenfranchisement that included the passage of laws regulating access to the ballot box and the use of violence. Today, we refer to this era as the era of Jim Crow, which was in full display from the 1880s through to the 1960s.
It really was. And, so as this Jim Crow era of our history was unfolding and inflicting its happenings upon a lot of people, the sky continued to evolve. Other things were changing too. So our next stop is in 1881, which is when the first electric streetlights were installed in the DC and Alexandria area at 15th and Pennsylvania Avenue, for those who are curious. And that impacted the view of the stars even more. So I'm going to add to the light pollution and drop the brightness of the Milky Way a little bit more so that we can see the effect that has on the sky. It really does impact what we can see. And then 1 year later, in 1882, there was a transit of Venus that was visible from the DC area, and that was on December 6th. So I'm going to get us into the morning and raise the sun. So a transit is what happens when a planet crosses directly in front of the sun. So it's kind of like a tiny eclipse. And transits of Venus were actually really instrumental in our understanding of the scale of the solar system. So transits of Venus happen more than a century apart because the orbits have to align perfectly. So there had been a transit of Venus a little over a century earlier, and that had been used to calculate the distance between the Earth and the sun. And it's kind of amazing, but you have to have a third object in order to do that. If you're just looking at the sun, not directly because you'll hurt your eyes, but if you're just trying to measure the distance to one other thing and there's nothing else interacting with it, you can't make a judgment based on that. But when something passes in between you, like the planet Venus, then you can use that to calculate the distance. And that distance turns out to be really important for then calculating other astronomical distances. We actually still use that unit, 1 Earth-Sun distance, or 1 astronomical unit, 1 AU, as the basis for a lot of astronomical distances. So I'm going to show the transit. So this down here, that little bright spot, that's Venus. And we've got the sun. And if I set time going forward a little faster than real time, we see the little shadow, perfect black circle of Venus as it crosses in front of the sun. So the sun is rising in the sky, which is why you see it shifting a little bit. But this is visible from Alexandria and also from multiple other parts of the world. So by having people travel to other places on Earth and all observe this same phenomenon to see where Venus crossed onto the face of the sun and where it crossed off the face of the sun, by observing that from different places on Earth, it allowed them to triangulate the distance from the sun to Venus and from Venus to the Earth, and therefore it allowed them to calculate and really refine that distance. Some of you may remember that there were 2 transits of Venus in the last 20 years, one in 2004, one in 2012. So those 2 were the next Venus transits after this one in 1882, because like I said, they're more than a century apart because of the planet alignment. So that's a cool daytime thing that we could see in the sky. And then in our next stop on the tour is going to take us into the 20th century to 1909. And it's going to take us to July, because by July of 1809, a new thing could be seen when you looked up in the sky, and that was an airplane. So July of 1909, the Wright brothers brought their military flyer to Fort Myer, Virginia, as a demonstration of its capability. And President Taft and his wife were there to see this flight. So that was the development of air travel. We had talked about balloons and everything, but the development of airplanes, the ability to travel that way, really had a ripple effect over the coming years and decades. And it was only a few years from the Wright brothers' first flight to aerial combat in World War I. So this was developing really quickly. But as of 1909, this visit came to the DC and Alexandria area. And so people living here would have been able to see an airplane in the sky when they looked up. And then within a year later in 1910, another bright, a new celestial spectacle lit up the sky, and that was Halley's Comet. That was one of the passes of Halley's Comet. It dazzled people for weeks on end. The tail stretched 2/3 the way across the whole sky. Stellarium does not give me a way to show that, but you can picture something bright and visible without a telescope stretching across a huge swath of the sky. And of course, comets can evoke many meanings, both positive and negative, but you can't argue with the fact that it is a really rare sight. So as we are in 1910, I want to take a moment and pause and see if there are any questions from the audience. You are welcome to put those in the chat or to virtually raise your hand if there's anything that you're wondering about up to this point. All right, cool. Well, then we shall continue the tour. So our next stop is in 1924. In 1924, as we're moving further into the 20th century, the pace of astronomical discoveries is really picking up as larger and larger telescopes are built. So a little earlier in the 1920s, astronomer at Harvard, Henrietta Swan Leavitt, had been using the large telescopes that were at Harvard's disposal to study variable stars. And in doing so, she figured out, so variable stars change in brightness. They get brighter and then they get fainter. And they take different periods of time. Some of them can take just hours, some can be days to go from bright to faint and back to bright. But Henrietta figured out a pattern. She noticed that the brighter a variable star was to begin with, the longer it took to go through this bright faint cycle. And that connection was a really big deal for astronomy, because it meant that if you could measure that amount of time to go from bright to faint, and you could see how bright the star actually looked, the amount of time would tell you how bright it should look. So if it doesn't look that bright, that means it's farther away. And so this combination, this connection, made it possible to measure distances to individual stars this way. That was really a new kind of cosmic yardstick, because we could measure the sun, Earth distance, and we could use the motion of the Earth to detect some nearby stars and figure out their distances. But for anything farther than that, we were just estimating. So this new cosmic yardstick, in 1924, some other astronomers, including Edwin Hubble, took this pattern, this connection that Henrietta Swan-Leavitt had made, and used it to measure distances to a number of things. And the first thing they did was to measure the distance to the Andromeda galaxy. They were able to find a variable star in Andromeda, and I just realized I need to make it be later. Andromeda's not up. There we go. So Andromeda had always been this sort of lightly visible fuzz blob in the sky. It's sort of this oblong, fuzzy shape. And by measuring the distance to a variable star in the Andromeda galaxy, what they announced in 1924 was, this is way too far away to be in the Milky Way. This is not a gas cloud in our own galaxy. This is a whole other galaxy. This is our neighbor in the universe. And this was really a revolution, because it meant that the Milky Way was not alone. It meant that what we had thought of as the extent of the universe was really just this one island universe, this pancake of stars amid many, many, many others in our universe. And it also meant that the universe was just a whole lot bigger than we thought. So this was a pretty pivotal year for that kind of astronomy. And the telescopes that were being used to figure out these cosmic yardsticks, this new ability to calculate distance with this cosmic yardstick got added on to our ability to measure how fast these other galaxies were moving. And astronomers do that by analyzing the wavelengths of light. And that will tell us whether it's moving toward us or away from us. And it'll tell us how fast it is. So as astronomers were measuring these distances and measuring the movement of these galaxies, they were kind of shocked to find that, first, basically all the galaxies were moving away from us. Andromeda is coming closer, we're moving toward it, but everything else, it's all moving away. And by looking at the distances, they realized the farther away a galaxy is, the faster it's moving away, which is weird. Because if the galaxies were just kind of floating apart gently, you would expect them all to be moving at similar speeds. The fact that the farther it was, the faster it was moving, that relationship implied it would only make sense if everything, the entire universe, was expanding outward. And if everything's expanding outward and we rewind time backward, that means that it all had to be together at one point. So this is where the idea of the Big Bang came from. And that really is the universe's ultimate origin story.
Shauna, you mentioned that all of this cosmic yardstick was based off of Henrietta Swan-Leavitt's contributions. How common was it for women to be astronomers at this time?
It's a really great question. So it was becoming more common for women to be professional astronomers. Very frequently, they were not allowed to continue working once they got married, or they had to be married to another astronomer. But Henrietta was one of a group at Harvard that were known as computers. So they were looking at photographic plates and making observations and comparisons. They were measuring those variable stars and doing a lot of calculations and important science work. A lot of the time, they were not allowed to observe at the telescope themselves or use the cameras and spectrographs, but they were doing astronomy. They were doing that work. One of the first PhDs in astronomy earned by a woman was in 1913, and it was Phoebe Waterman Haas. And I know that because my observatory at the museum is named after her, but it was 1913 when the first PhDs were awarded. But at that time, Phoebe still was only allowed to be a professional astronomer until she got married. So it was becoming more common. The computers, Cecilia Payne-Gaposchkin was doing her work around this time. So it was becoming more common, but the field was absolutely dominated by men. Certainly. It's a really good question.
Shauna, we're talking about the Big Bang being the universe's ultimate origin story. And it was around this same time during the first quarter of the 20th century that the historic preservation movement began, which has its roots in the creation of the lost cause narrative and its sympathetic interpretation of the institution of slavery in the American South. Ironically, perhaps, though, in 1925, Woodlawn was purchased by Senator Oscar Underwood, and he lived there until his death in 1929, and his wife, Bertha, continued to live there, and she died in 1948. But Oscar Underwood was a Democratic candidate for president in 1912, but lost out to Woodrow Wilson at the convention. And I find it fascinating that this senator from Alabama and a Democrat was well known for his anti-KKK stance. In fact, in 1924, he said, "It's either the Ku Klux Klan or the United States of America. Both cannot survive. Between the two, I choose my country." I also think that it's kind of ironic that he lost out to Wilson at the 1912 Democratic National Convention, and Wilson would go on during his first administration to screen the first motion picture at the White House. That was in 1915, and the movie was The Birth of a Nation, which is a movie that was a landmark movie for many, many reasons, but it was also a KKK propaganda film. And Wilson's support and thoughts about the film are disputed, but nonetheless, it sent a message that coincided with the rebirth of the KKK as an organization, which in 1924, by the way, was reported to have had as many as 4 million members. It also promoted on a scale never seen before that lost cause narrative I mentioned that so many early US historic preservationist work was rooted in. And during their time at Woodlawn, the Underwoods worked on restoring the historic site as part of that larger, broader preservation movement that was underway. And this larger preservation movement eventually led to the establishment of the National Trust for Historic Preservation in 1949 by President Harry Truman. I was wondering what kinds of new developments were happening in astronomy during this period in the 1940s.
Yeah, well, 1949 was a big year for the National Trust and for Woodlawn, and it was also a big year for astronomy. So let's scoot forward in time to 1949. I'm going to go to November, because in November of, oh no, I want to go to January. I'm on my wrong Hubble date. So in January of 1949, this was when the first official photos were taken by the 200-inch Hale Telescope. So the 200-inch was the largest telescope in the world for almost 50 years. It finally got superseded in 1993, but it began operations that year at the Palomar Observatory near Los Angeles. And its huge mirror could collect really large amounts of light, and that allowed it to capture these brighter and clearer images of these really faint and far away galaxies and nebulae. So I searched for Hubble's variable nebula. So that was, oh no, we don't want to bring the sun up. Let's go backwards till it's above ground. Oh no, that's Barnard's galaxy. Okay. See, the search window doesn't always work perfectly. right, where's the variable nebula? This is the great thing about Stellarium. You can just kind of course correct when you need to. All right, so this little fuzz blob here, this was the first official photograph taken by the Hale Telescope. But the Hale Telescope would go on to really revolutionize a lot of, again, this ability to see these faint, far away things, not unlike what we're hoping JWST will do to really change and expand our vision of the universe. So this is among many observations taken by this telescope, but this telescope was also getting better spectra, those wavelength analyses that could tell us how something was moving and how far away it is and what it's made of. And so all of those observations with this telescope allowed us to refine the rate at which the universe was expanding. And this is, the expansion rate of the universe is something we keep going back to. I talked about it before. We're still kind of refining it today. But the thing about it is that if you know the universe is expanding, if you know the rate, like how fast is it moving, and you know how far it has traveled, this is like the, a car leaves from New York going 50 miles an hour, what time does it get to, Washington, DC? If you know the rate and you know the distance it's covered, then you can calculate how long it's been expanding. And that gives you a rough age for the universe. So refining the rate at which the universe is expanding has been a focus for a lot of astronomy. And these big telescopes, like the 200-inch Hale Telescope that started operations in 1949, really added so much to our ability to make those observations. So astronomers today are still fine-tuning this expansion rate, and we've also now realized that it appears to be speeding up. It appears to not be constant. So that throws a whole new wrench in the works. But large telescopes like Hubble and hopefully JWST have and will give us this information. And the universe was not the only thing that was expanding at this point in time. Cities were also expanding, and that meant more electric lights and more light pollution. So I'm going to update our sky again. A little more light pollution. So we can still see stars. We're really only seeing the brighter ones now. So that brings us to our next stop, which is 1957.
Yeah, 1957 is a historic year for Woodlawn, Shauna. That was the year that the National Trust acquired the property. And it was the first property acquired by the National Trust. It was the first one it ever acquired. So not only was the universe, our knowledge of the universe expanding, the National Trust was expanding with its first acquisition of property, but also, as we've already kind of mentioned, cities were expanding. And I'm sure everyone is quite aware of this living in the Washington metro area, that expansion is something that doesn't seem to stop here. It's been expanding since it was created. And in fact, in 1966, as Interstate 66 was being constructed, to provide access to the newly developing areas west of the city, it was routed right through where the Pope-Leighey house, which is a Frank Lloyd Wright Usonian home, right where it was located. The home was originally constructed for Charlotte and Lauren Pope, who moved into it in 1941. And by 1947, it was purchased by Robert and Marjorie Leighey. So in 1966, when the interstate was being constructed, Marjorie made an agreement with the National Trust for Historic Preservation to save Woodlawn and to have it move from where it was to Woodlawn itself, to the property that is Woodlawn, so that the house could be preserved. This period from the 1950s into the 1960s saw all of this change going on, but it was also characterized by this ongoing competition between the United States and the Soviet Union. And so I was wondering, Sean, if you could tell us a little bit about that and how that was being expressed in through astronomy.
Absolutely. So 1957, big year for the Pope-Leighey house getting relocated, or getting, all of that was happening there. And 1957 was the kickoff of the space age. So October 4th, 1957, night sky, the first ever artificial satellite, Sputnik 1, was launched by the then Soviet Union, and it orbited the Earth for weeks. And around the world on the radio, people heard this. So this was a new thing to see in the sky, the first artificial satellite. And you couldn't really see Sputnik itself. You could see the rocket, the reflection off the rocket that was trailing behind it that was much bigger. But this was a big deal. And this set off a host of emotions: fear, determination, hope, plenty of other things. But it kicked the space race between the then Soviet Union and the United States into high gear. And within 12 years, people were walking on the moon. But this was a time with a lot of push to develop rockets, develop satellites and spacecraft, launch them, learn how to control them and maneuver them. And that meant a lot for human space flight, for sending humans into orbit and landing them on the moon. But it also meant a lot for pursuing that origin story. Where did our planets and solar system come from? And so we were able to fly the first spacecraft past a planet. Mariner 2 flew by Venus in 1962. And Viking 1, the first thing to land on another planet, Viking 1 landed on Mars in 1976. And it took soil and air samples. It was able to directly study Mars. And our solar system is this short list of things that we can actually travel to and get closer to study them. Stars and these other things, most of the things that Hubble is looking at and that JWST will look at, are far enough away that we're not getting closer. We're just studying them from this distance. But our ability to send things to space really helped us get these better observations. And again, studying these other planets helps us understand the origins of our own solar system. And that's really important. We want to know how planets form. We want to know how our planet formed, and that piece of how we came about. So 1957 was a really big kickoff for a lot of developments. And that sort of leads into our next stop, which is 1977. And this was a grand tour of the solar system. So if we go to August 20th, that is the day that the Voyager 2 spacecraft launched. And I'm saying Voyager 2. Voyager 2 actually launched first, about a week and a half before Voyager 1. There was some weirdness with the rocket, so they got switched. But this was, the timing of the launch was no mistake. The grand tour of the solar system used a rare alignment of the outer planets. And I'm actually going to show us that by leaving the Earth and going out into the solar system. So I'm going to show the orbits of the planets. I'm going to label the planets, get us kind of centered here. And then I'm going to zoom us out a little bit, zoom those inner orbits so that we can see the outer planets a little better. All right, so it's August 1977. So the Earth is here, so we launch our spacecraft. And if we look, we have Jupiter, and then Saturn, and then Uranus, and then Neptune. And they're in this alignment where we could send the Voyager spacecraft from the Earth, both of them. And as they flew by Jupiter, they could use Jupiter's gravity of getting close. That gravity would then slingshot them on to the next stop. So they both flew by Jupiter, got slingshotted onto Saturn. Voyager 1 then went upward and kind of out of the solar system because it wanted to get a good look at Saturn's moon Titan. Voyager 2 stayed in the line of the planets and it went on to Uranus and then Neptune. The Neptune flyby was in 1989. So these are the only close-up pictures we have of Uranus and Neptune. They were among the first close-up pictures of Jupiter and Saturn, and they gave us this chance to really study our own solar system close up. So the flyby of Neptune in 1989 that led right up to the launch of the Hubble Space Telescope. And that brings us to our next stop, which is in 1995. So Sean, while I bring us back to the Earth, what was going on at Woodlawn Pope-Leighey in 1995?
Well, Shauna, in 1995 and in 1996, they had moved the Pope-Leighey house to the site in the 1960s. And, about 30 years later, one of the things that had become evident that the site that they chose was a site where the ground was not really all that stable. So the house, which had been completely dismantled and put back together again on site in the 1960s, once again had to be completely dismantled and moved just a few tens of feet away from its original location so that it could be on more solid, stable ground. And of course, that's really important. They had spent all of this time and energy moving the house from the Falls Church area to Woodlawn, and then to discover that it was not stable. It had to be moved, otherwise the house would have been lost. So, and in a second attempt, and hopefully successful attempt to this date, at preserving that incredible house. And if you haven't been out to Woodlawn to see the Pope-Leighey house, I encourage you to do so. It really, to me, it's kind of interesting because it really captures some of that feeling of the 1950s and the 1960s. And, one of the things that Frank Lloyd Wright was really interested in was having his architecture blend in with the natural landscape, which, is, to me, is related to this whole idea of the night sky and gazing into the night sky. And what his work was doing, especially with these Usonian homes, is just bringing us closer to the outdoors, making the outdoors and the night sky part of the living space. So there was a lot going on in 95, 96 just to keep that Pope-Leighey house preserved and intact.
Yeah, absolutely. Well, and the 90s were an exciting time for astronomers too. The Hubble Space Telescope had launched in 1990 and then been upgraded in 1993. So somewhat like the Pope-Leighey house, it needed a little bit of adjustment to be stable and functional, but we got it there. And so that brings us to December of 1995, because at that point, the Hubble team picked, the telescope had been working for a few years. So the Hubble team picked the darkest, blankest patch of sky they could find. So this is the Big Dipper here, and a little bit out from the Big Dipper here, there's a few faint stars, but there's this patch where there's really just nothing, and nothing that we could see. And it's about the size of a drinking straw if you were to look at the sky through a straw. But blank area, no galaxies, anything else visible. So they pointed Hubble at that blank spot, and it stared at it for 10 days. And by leaving the camera shutter open for that long, it's like the ultimate long exposure photograph. It meant that over that period of time, the few little bits of light that might be coming from some faint object that's in that patch of sky would have time to collect on the detector for the telescope and become a brighter and clearer image. So this was called the Hubble Deep Field image. There has since been a Hubble Ultra Deep Field and the Hubble Extreme Deep Field, but this was the original. And after the 10 days, when the astronomers looked at their image of this blank patch of sky, it was completely full of galaxies, like thousands of them. And again, it was one of these revolutionary moments where we realized that these places we thought were empty are not empty. There is so much more in the universe for us to find. There's so much more than what we can see, and that these tools like Hubble allow us to find those things. And Hubble, the 30th anniversary of Hubble, everyone was waxing poetic about it. It has contributed to so many breakthroughs in our understanding that I cannot begin to list them all. There is not an area of astronomy that Hubble has not touched. It refined the expansion rate of the universe. It confirmed that black holes actually exist. It showed us star formation processes and supernova explosions. It showed us some galaxy formation and evolution. It showed us planet systems forming and allowed us to search for exoplanets that are orbiting other stars. So there's just no area of astronomy that Hubble has not added to, really. And it is still going strong, Hubble. 30 years, more than 30 years after its launch. And so that really brings us up to the almost present day, which is a moment about 4 years ago that I want to take us to. And that moment is August 21st of 2017. Because on that date, there was a total solar eclipse that crossed North America and was visible from a whole lot of different places. And this was a nationwide phenomenon, and I was so excited to get to help thousands of people learn how to view this eclipse safely, because this really was the first one that had been the first total eclipse that had been visible in North America for almost a century. And I've been cheating and scaling the moon up by 4 times, so I need to make it its actual size for this to work. There we go. So, so from here in the Alexandria area, it was a partial eclipse. It was visible. I'm going to speed up time so we can watch the moon kind of come in and so visible. There we go. So it came in and it got to about there. So that was about the most covered that the sun looked. Alexandria was not in just the right spot for the alignment to work so the moon would totally cover the sun. It still got noticeably darker. There was still certainly a lot to notice. But because we're in Stellarium and we can do this, I'm going to take us somewhere that could see totality. And that would be Charleston, South Carolina. All right, so here's the sun, here's the moon. I'm gonna play the same time lapse forward. Except I'm gonna stop it right there. So with the perfect alignment, the sky got dark at midday. You could see bright stars, you could see planets. And you could see the corona of the sun, this feathery upper atmosphere sculpted by the sun's magnetic fields, all of those lines and structures. For 2 glorious minutes, this was visible. And, you know, I loved how this eclipse really felt like a unifying experience. You know, no matter what your thoughts were about anything else happening in the country at that time, you could step back and be amazed by this thing that was happening that was really, truly bigger than all of us. And there we go. I forgot to pause time. It kept going and the moon kept moving there. So there was, you know, I still love how people will come up to me and tell me the story of where they were during the eclipse and what they got to see and how it affected them. It's as though it happened yesterday. It really sticks with you. And I also really loved how this eclipse drove home the importance of sort of citizen and community engagement with astronomical events like this. You know, people of all backgrounds wanted to observe it and, you know, knew that you shouldn't look at the sun, but they wanted to see the eclipse and everyone said it was really cool. So there was, you know, all of us who are astronomy educators really had to work together to make sure that everybody had the information and the resources they needed to view it safely. But this really was going to be sort of a whole country, whole hemisphere thing. And people across the country who were observing this eclipse from different places, you know, sent in their data, whether it was images or descriptions or even sound recordings of how animals changed or how, you know, just what was different during totality. So it was really this collective effort to make these observations and do this science that can only happen during a total eclipse, and that you really have to crowdsource. You need a lot of people in a lot of places to be able to catch these things. You can't just have only the professional scientists doing this work. So this type of knowledge sharing between professionals and, you know, citizens has happened in various ways over the course of science and many other disciplines. And it really has become easier. This kind of community engagement, citizen community science has become even easier with the dawn of technology and the internet and a lot of these new platforms that we have.
You know, so Shauna, you were talking about how you've heard people telling you their stories of the eclipse. So you get to hear my story. So I mentioned that I just moved here last week. Well, I moved from Charleston which is, of course, right in the path of the totality of the sun. So when you show this image, it's really familiar to me. It takes me back to being there. In fact, it gives me chills to go back to that and to remember it, because it was such an incredible experience. It was in Charleston that day. It was a cloudy day. And we were all really, me and my friends and my family were really just kind of bummed, because we were really concerned that we weren't going to be able to see it, and we were going to miss out on this once in a lifetime opportunity. And it was the coolest thing, because from where we were in Charleston, right in the city, as the moon started to get closer to the sun, the clouds really started to break up. And so for that full 2-minute period, or however long it was, we could watch this whole eclipse occur. And it was, I'd heard about how the birds would get quiet and crickets would start to chirp. And it was crazy, because that's exactly what happened. And, that 2-minute period of time, so often it feels like it just goes by so fast. But for me, anyway, that 2-minute period of time is like imprinted on my brain, and it seems like it lasted far longer than just a few minutes. It's such an inspiration. And the fact that it was able to bring out citizen scientists is not surprising to me. I think that there's such a much better effort these days, whether it's in the scientific world or in the world of public history, for scientists and experts to engage with people and to collaborate in their work together. It brings to mind our efforts here at Woodlawn to identify people that are descendant from all of those that once lived here at different times. Or in the case of the Pope-Leighey house, that didn't live at Woodlawn, but lived in the Pope-Leighey house, to learn from them and to collaborate with them and to share their stories, so that it's a much more inclusive site where more people can see themselves and their ancestors reflected in the stories that are shared there. And these efforts to engage, I think, really bring science and history alive for people in ways that, when I was growing up as a kid, didn't really happen in the way that they do now. So it's super exciting to see these opportunities and to experience things like this solar eclipse. It's something that is just indelibly imprinted on my brain, and I'll never forget it. It was absolutely amazing.
Oh, it is unforgettable. People always say you can't describe it, you just have to see it, and they're right. Yeah. So I would like to pause here for a moment and see if there are any questions. Okay. Because otherwise, I'm actually going to switch modes from showing you Stellarium to talking about JWST itself. So we have we've taken this journey through 240 years of the sky and of human history at the Woodlawn site in this area. And I want to take a look at JWST itself and how it's going to look back in time, and I think where it can continue the journey from here. So this is the telescope, and it is, we were just talking about community engagement. This is community engagement with both the astronomical research community and with the public is a big part of this telescope. There's, the data will all be made public, and there's already an early release science program. So for the first 5 months that the telescope is operating, they've selected scientists from across parts of astronomy that will each get some time on the telescope in that first 5 months to really see what it's capable of and see what it can show us. So that's really exciting. That's all going to be released in the next year. The telescope itself, first off, doesn't really look like a telescope. It's not a tube. It feels kind of strange, but it has what it needs. It has the mirror, and it has the protection from light. So the JWST is not really a successor to Hubble, because Hubble is looking at visible light, the kind our eyes can see. It can see a little bit of ultraviolet and a little bit of infrared, both of which are just beyond our visible spectrum. JWST is looking entirely in the infrared part of the spectrum. And it is, so infrared is light that our eyes cannot see. It's a longer wavelength. It's sort of past red. And we usually experience it as heat. Things that radiate infrared, you're radiating heat are emitting infrared light, including us, all of our bodies. We're creating infrared light right now. And so JWST is really the first telescope that is big enough and cold enough to see and detect the very faint infrared light that is coming from really, really far away galaxies. So the mirror and all the instruments on this side of the sunshade, so we've got the mirror, the primary mirror, secondary mirror, the instruments, the sunshade, all of this has to be kept extremely cold, like minus 388 degrees Fahrenheit cold, because if this is a telescope trying to detect infrared light, if the telescope itself is warm and is emitting infrared light, it's not going to be able to see anything in that part of the spectrum. So the sunshade, this 5-layer sunshade, protects everything on the cold side of the telescope. So the mirror, the instruments, all of that, the sunshade, and there's a cryo cooler, which is basically a space freezer, that keeps this thing at minus 388 Fahrenheit so that it can operate. The other side, the side that's facing the sun, is where the solar panels to generate power and the antenna to talk to the Earth. So there are things on the hot side, which is, it's in the direct sunlight, so it's going to be about 185 degrees. But it is designed to do this, to keep this cold area where it can detect this sort of thermal infrared light. So the telescope is set to launch on Wednesday, December 22nd. That is the current launch date. It will be launching from French Guiana because it is near the equator of the Earth, where the Earth is spinning a little faster. So that gives it a little extra push to get to its destination. That launch will be happening at 7:20 a.m. Eastern time. So I will be getting up to watch that. I don't know about you. And it's going to be seeking a lot of these answers to these origin questions that we've been talking about all through this journey. So the early universe, this is that Hubble deep field image. This is that straw-sized bit of blank sky that turned out to be full of galaxies and forming star clusters. So looking back to this period of time in the early universe, the first galaxies forming, early stars forming, Hubble could not see that because that light has been stretched to infrared to a wavelength that Hubble could not see. So JWST is going to be able to look back to these early baby galaxies that were the seeds of what became Andromeda, the Milky Way, and these other galaxies we see now. It's going to look at how those galaxies evolve over time. Do they merge? This is two galaxies in the midst of a merger. You know, how do they change? How does that affect star formation? How does that affect what goes on in that galaxy? Speaking of star formation, it's going to look at star life cycles. Stars like to form inside clouds of dust. Dust is really good at blocking light. The great thing about infrared light is it can see through dust. So in the way that a black trash bag blocks visible light, but if you look at it on an infrared camera, you can see right through it. JWST is going to be able to look through these dust clouds into these sort of baby star nurseries and see how these stars are forming and changing. And in those dust clouds, it's also going to be looking for planet formation. You have a star and there's dust around it. How is that clumping together to form planets? How might that be creating new little Jupiters or new Earths, or maybe planets that are unlike anything in our solar system? So JWST with this infrared view is going to really help start to unlock some of these puzzle pieces that up to now we have not had a set of eyes in the universe that could see it. I do want to show, so I have a little bit of a comparison. So here's Hubble in size, and here's JWST in size. So here's the mirrors. The mirror is quite a bit bigger than Hubble's, and the mirror size is light gathering power. The bigger your mirror, the fainter things you can see. And there's also a comparison of JWST with a standard tennis court, because that's about the size of this enormous sunshade. that is protecting it from the heat of the sun's radiation. And this is a little video that just animates how this telescope is going to unfold once it launches. So it obviously, you can't fit a tennis court inside a rocket. So it is folded up like an origami telescope. And then once it launches, so 31 minutes after launch, the solar panel deploys so that it can get power. And then the sun shield pallets unfold. And it has to do all of this by itself. It is already too far away. It's already past the moon. We can't send astronauts to fix it. It's got to do all this stuff itself. So the tower that's holding the mirror goes up. The momentum flap, which allows them to control how it's pointing and turning, unfolds. And then the big one, this is 6 days in, the sun shield. The sun shield is carefully rolled up and covered. The booms that hold it have to stretch out. It has to unfurl and tighten on both sides. It's got to do this without tearing anything, without getting stuck. A lot of the things that have been tested all this time have been getting the sun shield to unfurl correctly. Once it's out, then it's got to spread out. So there are 5 layers with empty space in between them. Why? Because empty space is the best insulation. If the layers are touching, they'll just conduct heat. If they're separate, the heat will not conduct. So now we have the secondary mirror that has unfolded so that it's out in front so we can catch what the big mirror sends to it. And then a really big deal, the folded mirror, the sides of the mirror have to unfold and place themselves so that they make the perfect curvature of that mirror. And then 29 days after everything is unfolded, it will fire its rockets and boost itself into the final orbit that it will be going into. And that final orbit is going to be past the moon. So this is not to scale. The Earth and moon are the right sizes, but definitely not the right distances. So Hubble is in a very low Earth orbit. It's right close to the Earth. It's just above the atmosphere. The moon is about 30 Earth diameters away. It's about 384,000 kilometers. So JWST is going to be out way past the moon, about 1.5 million kilometers. So it's going to be far. It's got to be far enough away that the heat being radiated by the Earth and the moon isn't going to affect the telescope. It's going to keep its sunshade always toward the sun. But at that distance, it can just stay so that the Earth and moon are kind of protecting it a bit from the sun, and it can see out into space to see these faint, faraway things that we want to look at. So that is this magnificent new space telescope that we are so excited about. And it's, you know, it's going to show us this period of time that we've really never been able to observe. It's a new kind of eyes that are opening on space really for humanity. And the hope is that it will continue this journey that we as humans have been on, connecting to the sky and to our origins.
Wow, Shauna, that's crazy to me. I had a couple questions for you about it.
Yeah.
And also want to ask others if they have questions to please, put it into the chat or raise your hand. Virtually use the Zoom raise your hand function. But so one of the questions that I had is, how long will it take for it to reach its orbit? Is that 30 days when that thrust occurs? That's what's going to push it to that. How long then will it take after that 30 days to get into where it will be?
Yeah, there's a whole timeline and sequence of what's going to happen. And so, yeah, all right. So it takes, all right. So it's going to take 30 days for it to reach the start of its orbit, but it's only going to take it 3 days to get as far away as the moon. So it unfurls everything, it boosts itself. So it's about a month to get it to that 1.5 million kilometers. But then there's the commissioning. So everything's unfolded, everything's placed, we're in the right spot. There's now like 4 months that we wait because the thing has to cool down. So it's there, it's unfolded, it's great. But now the cryocooler's got to do its thing and the sunshade's got to do it. And we have to wait for that mirror and everything to get cooled down to that minus 380 Fahrenheit so that it can then see the things that it's looking for.
So I guess that 4-month period will be this period for, especially the people that are involved with this project, of just like a lot of just on edge nerves, like hoping that everything goes okay.
Well, see, that first 30 days, that's really the nail biter, that's all the mechanical. It's got to unfold, it's got to click, the solar array's got to work, the sun shield's got to work. Once that's all in place, during the commissioning, when it's in that process of cooling down, they'll be testing systems and, testing stuff and checking on it. It is still, there is some nail biting, because until the mirror is cooled to the right temperature and the instruments are all cooled and it starts trying to make observations, until that sort of first light, we won't know for sure that it's all worked. Yeah. So there will always be some nail biting until that first observation comes back successfully, knock on wood. But that first 30 days is really, that's the nail biter for me. And then it's like, okay, it's working, we get it cooled down, we're good to
go. My second question that I had for you, and I see you've got a question that's coming up, so I'll, but let me ask you this question real quick. Are there any other satellite telescopes that are infrared telescopes? Is this unusual, or not?
Well, so there have been other infrared telescopes. The Spitzer Space Telescope, which was just, it finally ran out of fuel and it was discontinued. It's still in orbit. It's just not active anymore. That got discontinued, I think, maybe 2 years ago. But that was up for more than a decade, I think. And it was looking at a specific part of the infrared spectrum. So infrared light is a pretty big range of wavelengths. Then it was looking more at the near and mid infrared, which is closer to visible light, and it's slightly warmer things and closer and brighter. JWST is going to be looking much more into the far infrared, so these even longer wavelengths from these even farther, fainter things. So this specific wavelength, I don't believe we've ever had a space telescope look at it. And it's a wavelength. We do have some infrared telescopes on Earth, because certain wavelengths of infrared light can get through our atmosphere. But when you start getting out to those mid or long wavelengths, the atmosphere just absorbs them. So we can only see them from space. So there was Spitzer. There have been a couple of other, that's just the NASA ones. I know that I'm pretty sure the European Space Agency has launched at least a couple of infrared space telescopes, but nothing has yet been able to, again, to be big enough and to be kept cold enough to see, because the longer infrared wavelengths you're dealing with, the more the heat of the telescope is going to impact them. See. Oh, all right. So we've got any chance that the mirror will crack if it cools too fast. The reason they're doing the cooling down really slowly is so that nothing has that sort of thermal shock. It's exactly why everything, the unfolding, all that stuff happens real slowly and gently, so nothing gets jostled and nothing cracks. Absolutely. And how long does it take to get the pictures and signal back to the Earth? So the satellites communicate with the Earth at specific times. So they might need to be pointed one way to take their observations, and then we program to then point another way so that the antenna can talk to the Earth. Some satellites are taking observations and communicating at the same time. One that comes to mind is the Solar Dynamics Observatory, that's always staring at the sun and also constantly downlinking data to us. But for JWST, the signal, the light speed time for the signal to travel is less than, I think, 3 seconds. But they choose specific times to sort of take a bunch of observations and then send all the signals and kind of gather them all at once. So once things arrive, then it's just raw data, and it has to be processed into an actual image that looks like something. Because again, these cameras are looking at an invisible kind of light, so it already has to go through a digital process to take the information about where the infrared light is and give it a color and make it into an image that we can actually see. So The initial data, I believe, after that first 5-month period, there is a release date for sort of the big, big announcement, first observations. And so that'll be a few months after it kind of reaches its orbit and is working, but it'll all be stuff to look forward to. And can the ISS see JWST? No, JWST is going to be far enough away and small enough that it's not something that'll be kind of visible as a dot in the sky. It's a little too far away for that. But, are the Europeans, Chinese, or Russians doing anything similar? All of the space agencies are doing various things. I don't know off the top of my head. I don't know for sure. I can't think of any specific plans for infrared astronomy like this. One of the things about astronomy being sort of a global pursuit, the sky belongs to everybody, it's visible from everywhere. Space and astronomy is one of these places where there's actually a lot of collaboration. So the fact that NASA has built and is launching this telescope, it's going to be usable by scientists from all over the world. So it is a resource that is shared. And it's taken how many $1 billion and how many decades to design, build, and get hopefully launched. So when you have a resource like that that's really groundbreaking, that's a resource that's going to be shared, and it's not expected that every space agency would make their own. Now, some space agencies may choose to; they may want to do it their own way. I don't know of any off the top of my head. Do we know what the very first observation target will be? They probably do. They have not announced it. So whatever the first image is going to be iconic. Like in much the same way that the Hubble Deep Field image is absolutely iconic for astronomers. The first JWST image is going to be a big deal. So I'm confident that they will choose something that has shape, that is visible and understandable to all of us who are not the scientists working on it, and that it'll be something that they can clearly explain for sure. Oh, will it be in the same orbit forever? Will it move out of the solar system? So it will stay in that same orbit. It's at a specific point called L2 it's sort of a gravitational balance point between the Earth and the sun and the moon. So it's almost like a gravity well. You know how if there's a lumpy surface and you have a ball, it's going to kind of settle into the depression. It's sort of like a gravitational depression, and the telescope it'll be orbiting around that point, but it will stay in that orbit in a stable manner. So it is not, unlike the Voyager missions, it's not going to be moving outward constantly. It's going to be staying at that same distance. Oh, any concerns about space junk collisions while it unfolds? Space junk is always a consideration. It's going to stay in its sort of protective area through, I think, low Earth orbit and get, almost out, a little closer to the moon before they start unfolding things. The most space junk is really close to the Earth. We have most of our satellites in low Earth orbit. So once it's past that zone, the chance of it getting hit by something gets smaller. Like all satellites, it has, and especially all recent spacecraft, it's been designed to withstand that. So there is micrometeorite protection, the mirrors, all of those pieces are built to withstand micrometeorite strikes, because it is expected that over time in space, something will hit it. During the unfolding, we're really hoping, the chances are low, not zero, but the farther away it gets from Earth, the less chance it will have to run into artificial space junk, at least.
There was a question about whether or not changes in the night sky or the day sky had any impact on enslaved people, and whether or not it made any differences in their workday. And so to answer that question really quickly is that it would have not had any different impact on them than it would anyone else. And whether or not it would have made a difference in their workday, it depends on the phenomenon, I would imagine. I don't know for sure, but I would imagine, and I don't know when the last total solar eclipse was that was visible from someplace like Charleston, but I would imagine that would be time for just about anyone to pause. As Shauna was saying, these celestial events are experienced in ways that sometimes seem to bring people together, perhaps. And so I can only imagine that if I were out and something like that was happening, I would definitely be looking and watching and observing. So I would imagine that it did create these kinds of events could create some kind of impact on a work day. But really, I think one of the things about that is it really depends. In the case of someone who is enslaved, it really depends on the person who's doing the enslaving as to whether or not it has any real impact on that person, positive or negative, since so much of that person's life was in the hands of someone else. So that's a great question. And
Really is.
I think that if you have any other questions, we have Shauna's email, and she'd be more than happy to answer any questions that you might have. That's been dropped into the chat. And I just wanted to say on behalf of Shauna and the folks, Shira and I here at Woodlawn and Pope-Leighey House and the National Trust for Historic Preservation, I want to thank you for attending this evening's program, which was made available for free with support of NASA and the Smithsonian's National Air and Space Museum. I want to thank Shauna so much for all of her hard work in putting all this together. If you found this evening's program to be valuable to you, please consider making a donation to Woodlawn and Pope-Leighey House at Woodlawn Pope-Leighey House, all one word, .org, and select donate on the top menu bar. And please have a safe and wonderful evening, and we look forward to seeing you in person at Woodlawn. Thanks a lot, everybody. Have a good night.
Thank you all so much.